Today, we open the box. Every course tells you to call fit on a model and move on, and that line hides the single most important idea in this entire field. So today, you're not going to call it. You're going to write it, the actual learning algorithm, by hand, in about 15 lines of NumPy. No library doing the work for you. Just you, a loop, and two derivatives. By the end of this one, you'll also know why a model that's right 73% of the time can still be worthless. That sentence will make complete sense in about 10 minutes. I'm Rohan Singh, this is CloudNimbus, and this is part 5, How Machines Actually Learn. Quick recap, because everything today builds on it. Capital X is your features, the columns a model is allowed to look at. Lowercase y is your label, the answer you're trying to get out. Features in, label out. Now, a word we've been using loosely since part 1, model. What actually is a model? Strip away the mystique, and it's remarkably plain. A model is a function, an equation, with a handful of adjustable numbers inside it. Training a model means nothing more than searching for the values of those numbers that make the function's guesses match reality as closely as possible. That's it. That's the whole secret. Today you build that search from nothing. Before you can improve a guess, you need to measure how bad it is as a single number you can watch go up or down. That number is called the loss. Here's the idea in plain English, no notation yet. For every point of data, take the model's guess, take the true answer, and find the gap between them. Square that gap, so a miss in either direction counts as a positive amount, and a big miss counts for a lot more than a small one. Then average that squared gap over every single point you have. That average is your loss, and this particular flavor has a name, mean squared error. In notation, mean squared error is 1 over n, times the sum of every prediction minus its actual value, squared. That's exactly the sentence I just said to you, written with symbols instead of words. Lower is always better. 0 would mean every single guess landed exactly on the true answer. So we have a way to measure how wrong. Now, how do you actually get less wrong? This is gradient descent, and I want you to picture it before you see a single formula. You're standing on a hillside in thick fog. You cannot see the valley floor, and you cannot see the whole landscape. But you can feel, right under your feet, which direction is downhill from exactly where you're standing. So you take one small step in that direction. Then you stop, feel again, and take another small step. Repeat that enough times, and you walk yourself all the way down to the bottom of the valley, without ever once seeing the whole map. That feeling of which way is downhill has a precise mathematical name, the derivative or the gradient. That's genuinely all it means here, which way is downhill from where you're currently standing, and how steep the slope is at that exact point. You do not need to be able to derive one by hand to use this. You need to know what it's telling you, which is exactly that sentence. And the size of each step you take has a name too, the learning rate. Make it too small, and you're inching down that hillside all day, technically making progress but taking forever to arrive. Make it too big, and you don't walk down into the valley, you leap clean over it, land on the far slope, and bounce back and forth, getting worse before it gets better, sometimes never settling at all. Somewhere in between is a step size that gets you down efficiently. Finding that sweet spot is a real, practical skill, and you'll feel both failure modes yourself in the lab today. I want to say this plainly, because it's easy to let a moment like this slide past. This loop, measure the loss, feel which way is downhill, take a small step, repeat, is the algorithm behind essentially all of modern AI. The same basic idea trains a 2-number linear model on your laptop in a second, and it trains large language models with billions of parameters over weeks on enormous clusters of computers. Different scale. Same walk down the same kind of foggy hillside. Let's build it. Open the notebook, nothing installed, same as always. The setup. Imagine you're guessing salaries from years of experience. We invent 60 people with a secret true relationship. Salary equals 8 times years of experience, plus 30, and add a bit of realistic noise, because no real person sits exactly on a straight line. Crucially, the model is never told that secret rule. It has to rediscover it purely from the 60 dots. A straight line is y hat equals w times x plus b. W is the slope, how much salary rises per year of experience. B is the intercept, the starting salary at zero experience. Our whole model is those two numbers. We start with a deliberately terrible guess, both set to zero, which draws a flat line sitting nowhere near the data. We compute the starting loss with the mean squared error function we just described. It's large because that flat line is a bad guess, and the loss is telling us exactly that as a single honest number. Now the gradients, the which way is downhill for each of our two numbers, W and B. I'm handing you the two formulas rather than deriving them live, because deriving calculus isn't the point of today, using it is. Two lines of NumPy, and we have our compass. And here's the loop itself. Predict, measure the loss, compute the gradients, nudge W and be a small step downhill, and repeat 2,000 times. Watch the printed loss as it runs. Step 0, a big number. By 400 steps, much smaller. By the end, barely moving at all, because we're close to the bottom of the valley. This is the single most important plot in machine learning, full stop. Every model you will ever train, this tiny two-number line, a decision tree, a neural network with 1 billion parameters, is fit by watching a curve exactly like this one fall. And here's the number I want you to actually remember. Our handwritten NumPy gradient descent converges to a slope of 7.969 and an intercept of 28.916. The true values we hid from it were 8.0 and 30.0. It got extraordinarily close, using nothing but the dots and that hillside in Fog Walk. Now, the same job in 3 lines, using scikit-learn's actual linear regression. Fit it on the same data, and print its slope and intercept alongside ours. 7.969 and 28.920, practically identical to what our 15-line loop found by hand. Linear regression. Fit was never a different idea. It's the same search, down the same hillside, just written in faster, more careful code. You now genuinely know what the library was doing the whole time you were calling it. Now, the part I most want you to sit with. This is the most valuable 10 minutes in the whole series, and it starts with a number that looks perfectly respectable. We move from predicting a number to predicting a category. Will this customer churn, yes or no? That's classification, and it needs its own algorithm, logistic regression, despite the name, and its own way of grading success. We train it on 4 numeric columns from our churn data: tenure, monthly charges, total charges, and whether the customer is a senior citizen. On customers it's never seen, it scores 78.42% accuracy. That looks like a solid result. Now meet the laziest possible model. A dummy classifier that doesn't examine a single customer. It doesn't look at tenure, doesn't look at charges, looks at nothing at all. It simply always predicts whichever answer is most common in the training data, in our case, always guessing this customer will not churn. That model, which has learned precisely nothing, scores 73.46% accuracy, and it catches 0 churners, not a handful, 0. 0% recall because it never once predicts churn for anybody ever. Sit with that gap. 73.46%, doing nothing whatsoever. Our real trained model only edged it out by about 5 points to 78.42. On an imbalanced problem like this one, where most customers simply don't churn, accuracy on its own is close to meaningless. A company could deploy the do-nothing model, quote a 73% accuracy figure in a slide deck, and it would sound almost as good as real machine learning, while silently protecting not one single at-risk customer. So we need better scorecards than accuracy, and there are 4 boxes every prediction can land in. Predicted stays, actually stays, a true negative, fine. Predicted churns, actually stays, a false positive. Predicted stays, actually churns, a false negative. Predicted churns, actually churns, a true positive. Precision asks, of the customers we flagged as at risk, what fraction really were? Are we crying wolf? Recall asks, of the customers who genuinely churned, what fraction did we actually catch? Are we missing people? Put it in business terms, because that's the only version that actually matters in a meeting. A false positive is a retention call or a discount offer sent to somebody who was never going to leave, mildly wasteful, a bit of wasted budget. A false negative is a customer who walks straight out the door while your model is telling everyone in the room that everything is fine. That customer's entire future revenue is gone, silently, and nobody even tried to save them. So which mistake costs more, the wasted retention call or the customer who leaves unnoticed? I'll tell you honestly, it depends on the business, the size of the discount, and the value of that customer. That's not something a metric decides for you. That's a decision a person has to make on purpose before a model ever ships. Our logistic regression scores 78.42% accuracy, 62.96% precision, 45.45% recall, and an F1 score of 52.8%. And now, unlike 5 minutes ago, you actually know what each of those numbers is accusing the model of. One more idea, and it's one you have to see happen rather than just be told about. A decision tree, left completely unrestrained, will keep asking yes or no questions about the data until it can carve out a rule specific enough to fit every single training customer almost perfectly. Trained with no depth limit at all, that tree scores 99.06% on the data it trained on and 71.75% on data it's never seen. A 27-point gap. That is not learning. That is memorizing the noise in 3 sentences. Now we put a leash on it, a maximum depth of 4, limiting how many questions deep it's allowed to go. Training accuracy, 78.91%. Test accuracy, 78.28%. The two numbers sit right next to each other now. That gap closing is overfitting, undone in front of you. Sweep every depth from 1 to 20, and you can watch the whole story unfold in one picture. Training accuracy climbs steadily toward 100% as the tree is allowed to grow deeper, pure memorization. Test accuracy rises for a while as the tree learns genuine patterns, peaks, and then actually falls as extra depth starts fitting noise instead of signal. In our sweep, the best depth turns out to be 5, at 78.85%. And underfitting is the mirror image of all this. A tree so shallow it hasn't learned enough of the real pattern yet, doing poorly on both the training data and the test data alike, because it genuinely hasn't found the signal. The goal was never perfect on the training data. The goal is the sweet spot in between too shallow and too deep, and the only honest way to find that sweet spot is the sealed envelope from part 1, the customers the model never sees until Judgment Day. Everything we did today, we could only trust because we never let training data mark its own homework. So, what do you actually own now? A gradient descent loop you wrote yourself that landed on almost exactly the right answer. The honest meaning of loss, derivative, and learning rate, no hand-waving left in any of those 3 words. Proof that accuracy alone can lie to you, and the confusion matrix vocabulary to catch it. And overfitting, seen with your own eyes as a gap between 2 numbers, not just asserted at you. Homework 1. Rerun the from-scratch training with a learning rate of 0.001, then 0.03, and watch what each does to the loss curve. 1 crawls, 1 can blow up entirely. 2. Compute recall and F1 for the dummy classifier, not just its accuracy, and really look at what its recall is telling you. 3. Using the depth sweep, find the shallowest tree whose test accuracy sits within half a percentage point of the best one, and post that depth in the comments, along with why the shallowest good enough tree is often the smarter choice than the single best score. Part 6 is the professional workflow, pipelines, encoding every column properly instead of just 4 numeric ones, cross-validation, and automated tuning that finds that sweet spot for you, so you never have to eyeball a chart like today's again. Subscribe so it finds you, and the full guided course with graded exercises is on Udemy through CloudNimbus, linked below. You wrote a learning algorithm by hand today, and you caught a lie that accuracy alone would have told you. I'm Rohan Singh. This has been CloudNimbus, and I'll see you in part 6.